All right, welcome back to another EMP session today. I hope you guys enjoyed your break on Tuesday. So today's topic, we're going to be discussing recursion, which I think you might have covered this week. As always, you can follow along on the course website, and we're going to use the playground on the 125 website to do the code. Feel free to ask questions in the chat as usual. Since we have a small crowd today, you know, we can make this go at your pace, at a comfortable pace for everybody. All right, so let's get right into the topic, which is recursion. So recursion is kind of a different way of solving your typical programming problem, right? So usually when we teach you to take an approach to this, we say, think about how you solve it with hand, like pencil and paper, kind of like an intuitive approach. And these approaches are typically like the iterative solution to solving a programming problem. However, an alternative way of thinking about it is recursion. So it's really all about breaking down the problem into smaller pieces, identifying a base case, and then some other simpler versions of the case that allow a method to be called on itself. So the method will call itself again to solve the original problem. So kind of in that definition, I guess there's two steps really. There's identifying the base case, and then or base cases, and then identifying the smaller versions of itself that you can break it down into to call the same function over and over again to achieve a new result. So let's take a look at kind of the most famous way of accomplishing this, which is the Fibonacci numbers. And I think most of you are probably familiar with it if you took a mathematical class. I think it's covered in the class lectures as well. 125 lectures, I mean. So you can, this is kind of the formula. So Fibonacci number, f of n is equal to f of n minus 1 plus f of n minus 2, where n is kind of the nth Fibonacci number. There are some special cases, of course, where f of 0 is equal to 0, so it's not really dependent on the two previous numbers, and f of 1 is equal to 1, again, where it's not dependent on the two previous numbers. So this is the recursive solution for it, or how to find the Fibonacci number of, if you're given like an n to n. And so you'll notice that we've broken this down, like I mentioned, into kind of the two base cases, which are the special cases where the method does not follow a pattern, and then kind of a generalized rule where the Fibonacci method is called again, but using a different input. And that's important, right? If you're going to call Fibonacci again and you use the same input, we're going to end up going infinitely. And if you don't have base cases, we're also going to keep going because you can always continue to go less than n, 1 less than n, and 2 less than n, right? And if you look at like the number line. So it's really tricky here when you're creating recursive functions to ensure that you have a base case and to ensure that you don't call the same function over and over again without changing the input somehow. So this is the recursive solution. We can take a look at the iterative solution. Okay, So that is the iterative solution. So again, this is maybe how you might approach it if I told you to solve the problem. Let's just say that you didn't know how to do recursion. What would your approach be to solving the problem? And you might think, okay, if it's 0, 1, return 0, 1. And then you might think about how you would do the math to get to the Fibonacci number using some for loop, which is great and all. This is significantly more code than it's over here. And it's a little bit more difficult to understand, right? Like it's not as simple as this approach is. So recursion is often good because it's a little less clunky to work with. It would be easy to make mistakes in this example, for instance. I don't think I've ever implemented the Fibonacci number sequence iteratively. Hence, like if I looked at this code, it would take me some time to understand what was going on here. But here it's a little bit easier because you know what the formula is. You could see how it directly correlates to the recursive solution. So yeah, I guess what I was trying to get to there is recursion provides a slightly so it provides a slightly more elegant way to solve the problem. And I think Jackie was saying here that when he tried to implement this approach, it took considerably longer, and it's easier to make mistakes in this case, right? Recursive solutions, I think you choose them when there's like a very easy way to break the problem down into smaller chunks. I think that's your question in the chat. Which is just easier to write and easier to do, and it's an easier way to solve the problem. And in that case, you would choose recursion. Yeah, I would say anytime that I see any type of like easy to break down problem with the base case and everything, I just automatically go for recursion rather than the iterative solution. But they're also tricky, right? Like you can't see if you can't easily see what happens with this call of the Fibonacci n-1 and the Fibonacci n-2, which is why I think some students would prefer not to use recursion, because you have to think about the call stack, right? You have to think about what happens after this n-1 is called and n-2 is called. What is the result in those cases, and how do those add up back to get the final answer? So even though it is kind of an elegant solution in those cases, it's also harder to understand from someone who doesn't know what the implementation rules are. And that would be the only reason why you wouldn't do it. Okay, recursion is difficult. Don't worry though, we'll walk you through it. We have several practice problems. Okay, so here is the first question. So we're going to be searching through a linked list recursively. We've provided the iterative solution to what we're looking for, right? You can think in how would you approach this if you were just, if I gave this to you today, and you would be like, okay, I would write a for loop that would maybe go from the beginning of the linked list till the very end, and at every single node in the linked list, I would compare the values. And if the value returned what I was looking for, then I would return true. Otherwise, I'd return false. That kind of approach is the iterative approach. Now think about how you might solve this using recursion. We've provided some starter code for you, which you can just copy and paste right into the playground. And then we've also provided some pseudocode that you can very easily kind of think about to understand what needs to be done. So this is going to be the function that you guys will primarily implement. This you also need. So this is the function that is called, contains, and then contains calls contains helper again. So this is kind of the pseudocode that you'll have to figure out. What case when do you need to stop, right? If you were searching through a linked list, when do you know you have to stop and return a value? And then if you decide not to stop and return a value, what do you typically do? Like, what does a for loop do in the other case? Which is check the rest of the list. So how would you write that in code? So we'll do 15 minutes for that one. 13 now, so we'll do 6. We'll do 6:30. Yeah. The if statement would be state start value equal value. That's correct. Sorry, I didn't mean to spoil anyone's solutions if you're working through the recording. And let me know when you've finished implementing it and this test case works and everything. Okay. That was a lot faster than I think he was expecting. Yeah, I mean, your solution looks correct. The if else statement. I'll go ahead and move your code over. See if we can pass to your solution. Okay. I'll add the two functions that we provided here. And I'll add test cases at the bottom. And then I will add your solution. All right, so the base case is, thinking, when does this loop stop, or when do we need to say we found the value that we're looking for? And you can do that by doing start.value, which is value, and then see if it equals the value. And if that's the case, then you return true. So we've accomplished the base case. Then in the rest of your else statement, you put a return contain help. Start on that. Yeah. So if you haven't found the value, you want to figure out how to find the next value. And you can always use the dot next, right? Remember in our iterative solution, we just went to the next value like this. And that is what becomes our new start value. So start dot next gives you the next value in the linked list, and that becomes the start value when you call contains helper again. And yeah, so then let's try to run it. Oops, I ran the wrong thing. Contains helper. Line 42. Okay, and there's a textile error right here. What does that mean? I'm gonna rename this to num. Oh. Um, I am not sure why we're getting that textile error. If you see why, then let me know. Start hide a field. Okay, I'm going to call this something else. All right, let's do node and node here and node here. Doing more. Okay, looks like that fixed the issue. Now we are running into a null pointer exception because it cannot read the field value parameter 2 is null. Okay, so now that we've taken care of that, what is the other thing that we need to think about, because this is a linked list, right? So you're running through your contains helper function and you're giving it a number each time and a node each time to check, right? So it's checking the nodes and it comes along to the very last node, right? Because you keep doing node.next. How, in the event that you get to the very last node, like we're past the end of the linked list, you end up with null, right? An item node is null now. Now we're running into this error because we're trying to access a value instead from the null. So you got to think about kind of an additional layer on what needs to be done here to handle that case where you search the entire list and you can't find the answer. Any ideas on how we might handle that? If you had a node that was null because we had reached the end of the linked list, right? We had been calling contains helper every time because the number doesn't exist. How would you write the solution so that you handle that instance also? Any thoughts? Let me know if that's not clear. You could use an assert, or you could do an if statement or something. So yeah, that's one way to handle it. So I'm going to use I'm going to use an if statement though, because instead of asserting kind of that node should be null, I would want the function to return false, right? Because I know it doesn't exist in the list. I don't want to say, I don't want to return an error at that point. I want to return false. Yep, there we go. That's kind of the other hidden thing that we didn't mention in this pseudocode. So just to review, what's happening here is we've pretty much got two base cases, right? Two cases where we know we want the function to return something. First case is we didn't find the value inside the list at all. So we've reached the end of the linked list, in which case we know the node is equal to null and we return false. The other case is if we found the value, so we're at each iteration of the recursive function, we're checking to see if the value is in the node. I mean, the value, yeah, if the value is in the node, and if so, we return true. And then after those two base cases are considered, we say, okay, I'm not at the end of the linked list and my current node is not what I'm looking for, then let me go to the next node. And that is what we're doing in this final line of code here. And we've produced the correct results. So let's move on. Okay, here is our next recursion problem. So we attempted to create a recursive solution for this function here. In this function, it takes in an array and it adds up all the elements of the array. And I'll copy and paste this here. Oops. Copy and paste this up here. Okay. Now your goal is to figure out what's wrong with that solution. Why are we getting in errors here? Might be helpful to check out the base case. What are the base cases? And it might be helpful to check out the sublist documentation, which I also have linked on here, so you can go check that out. Okay, this is not the actual documentation, but this will do. All right. So we'll do 15 minutes for that one. So we can regroup at 6:45. Otherwise, you can just let me know when you finish. And I'll figure it out. All right, so it looks like we've got a solution. Your solution looked good to me. Let's try it out, I guess. All right, let me copy the code again. Okay. All right, so the first error that I'm kind of getting right now is some incompatible types between integer array lists and lists. So I think I'm going to change this to the array list up here. Get rid of that. Okay, we got rid of that error. Now it's giving some indexing problems. All right. Now let's think about the recursion parts of this, right? So right now, what we're doing is we're taking the array list, got 3 elements in it, we're taking the 0th element, and then we're summing, we're calling the sum function again for the sublist from 1 to array.size minus 1. And if you looked at the documentation for this, I think it goes up till the endpoint, but it like the from index is obviously the beginning of the sublist that you're wanting to sum, and the to index is going to be the end of the sublist, except you don't want to include that. It's exclusive, so you don't want to include that last value. So if you do array.size minus 1, we'll be including everything from 1, so which is the next element in the array list, up till the last element, but it won't, but that won't be enough. I think you have to go all the way up past this to array.size. So if I get rid of the -1, all right, so now we're getting somewhere. And now it's giving me a different error, which tells me that index 0 out of bounds for length 0. Now you think some more about what kind of base case would you want. So if you think about how this sum function works, the first time it's called, right, you're saying array.get0, which is 1, and you're saying 1 plus the sum of the array from 2 up to 3, 2 comma 3, that would be array. And when this sum 2 comma 3 is called, that ultimately ends up being a 2 plus the sum of 3 up to the end. That's it. So, and that's called, then you do 3 plus the sum pretty much till nothing. And now we're running into an error where you're getting an index 0 out of bounds because it's an empty array. There is no index 0. So that's kind of what the call stack looks like. If you're wondering. At this point, we have to figure out how do we just take a look at the array size, and using the array size, maybe we need to tell the function when to end, right? If we leave it as is, it's just going to continue looping forever. And if it does that, you are indexing at indexes that don't exist. So as you have in your solution, what we might be interested in doing is maybe we want to specify when we've reached one element in the index, right? If we know that we only have one element in the index, in the array list, then we know that we can just add that last thing and we don't need to call sum again after that. So we're just going to do array there. So we've got one thing in here. And so instead of doing this stack, we're going to get rid of this and we're just going to do that. And now run this. Sorry, that size equal to 1. Are we running the error still? Oh, sorry. That was a dumb mistake. Make sure you return. Otherwise, it's just gonna. Okay. And now we get the right answer, which is 6. So yeah, so let's just really quickly recap. What changes did we make here? We had to figure out how we need to do the indices for sublists. So sublists go from whatever the beginning index is up till the last index exclusive. So this last number needs to be not the, and it shouldn't be like the very last thing inside of the array. It should be one more than that, basically. And then we thought about what the base case would be, which would be the case when the array is 1, has a size of 1, because then we just need to add that last number to the kind of the stack, and we can just return that. And we don't need to continuously call sum at that point. So that's the base case. And then what is the last thing? I think that's everything. And I like that in your solution, you checked to see if it was null, which is also good. If it's null, just return null. We didn't specify that in the code, so it's not necessary. You didn't add that. Yeah. Cool. So let's keep going. So here's the last question for today. We're going to be looking at Fibonacci numbers, which is similar to Fibonacci numbers, except now you have kind of 3 different things that make up the nth Fibonacci number. So if you have the nth Fibonacci number, it is equal to the one less than that number plus 2 less than that number, not 2 less than, but like the n-1 Fibonacci number and the n-2 Fibonacci number and the n-3 Fibonacci numbers. All 3 previous numbers in the sequence are added together to get the nth Fibonacci number. And then we also have some base cases. So if the Fibonacci, the number n is 0 or 1, you return 0, not return. Sorry, gave that away a little too soon. But if you're looking for the 0th or the first Fibonacci number, that would be 0. If you're looking for the second Fibonacci number, it would be 1. So we talked about the Fibonacci number sequence and how to implement this recursively. This should be fairly straightforward. If you can do this without looking at the implementation for the Fibonacci number, then that's great. Yeah, so let's do that. There's no pseudocode. We'll do that for like 5-10 minutes. If you finish earlier than that, let me know. All right, looks like we've got an answer. Looks like it's the correct answer to me. Do you want to perhaps explain your code, or if you're not interested, I'll just jump into the explanation, but if you want to explain your code, that would be awesome too. I can post it on the screen. Okay, I'll take that as you can go ahead and explain it. So I will, okay, rather than posting your code, I'll just go through the implementation. All right, so just like with Fibonacci numbers, you know that your return type is going to be an integer, except now you have the Fibonacci. Fibonacci. Okay. Now you have the Fibonacci number, and I'm putting in an integer n. So, okay, let's think about how this will, usually go, right? If you're implementing like a recursive function, you're going to want to identify the base case. And in this particular scenario, you've got two base cases, right? This is one, and this is the other. So base case 1 and base case 2. So in base case 1, n is equal to 0 or 1. In base case 2, n is equal to 2. And finally, you have the other case, which is this one. Recursive case, I guess. Recursive case, which is n is kind of equal to n minus 1. Or I guess you could say, yeah, and trib of n is equal to trib of n minus 1 plus trib of n minus 2 plus trib of n minus 3. Okay, so that, I think those are the three things you need to do in order to find the final Fibonacci number. So this is just kind of an if conditional. That's all you need to set up here, right? You have to figure out how to do the ORs for this case. Right, simple, straightforward kind of thinking. Return 0. Right. So in the other case, this is going to be C. If n equals 2, then you want to return 1. And then finally, here, we've literally written out the code for you in this bigger code. And in that one, you're just going to call the Fibonacci. Right? If you don't meet any of these conditions, you just want to call Fibonacci on the n minus 1 and add that to the Fibonacci on the n minus 2 plus the Fibonacci on the n minus 3. Okay. Oops. Okay, I'm missing semicolons everywhere. So that's the gist of it. Am I missing something? No, that looks right. Yeah, I think it's just looking for a class or an interface or something. Yeah, so that's it for the Fibonacci question. And yeah, you've done recursion now. You now understand the programming jokes on programmer humor, our programmer here. And then there's, of course, this great little meme right here. That's all the content I have for today. Thank you for stopping by. Always appreciate having an audience. We're almost at the end. Good luck on the MP. And have a nice day.